Avogadro's law. Where have we heard Avogadro's name before? That funny unit, moles, and his funky number, 6.022 times 10 to the 23rd. We actually got our concept of particles and moles from his work with gases. So Avogadro studied the relationship between the amount of gas and the volume of a gas. So what he did was he measured the volume of a gas at constant temperature and pressure while varying the number of moles of gas. So think of a balloon, and you put more air into the balloon. What does that do to the volume? It goes up. That only makes sense, right? So we see that if you increase the number of moles, the number of particles, the amount of gas, the volume increases, and it increases in a linear fashion. So Avogadro was actually born the same year our country was born, 1776. What was really groundbreaking about this is that the volume wasn't proportional to the mass of the gas. It was proportional to the number of particles, the moles. And this was a big new idea. So volume is proportional to N. N is the variable we use for moles of a substance. Well, I kind of already talked about that. You blow more air into a balloon, it goes up. That just makes sense. So, kind of a mistake in the slides. A more mathematical statement of Avogadro's law would be like that. V1 over N1 equals V2 over N2. So let's do an example. A 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? And this is one of those slides that I really should change, because this problem is a little bit tricky. But I'm going to teach you how to do it. Question? What's N? N is the number of moles of the gas. I'm going to teach you how to do this problem, so when you see it on an exam, you shouldn't be tricked by it, because I taught you how to do it. You got a question?
So I thought the volume of the gas was dependent on its container, not how many moles it had. Like, even if you only have a little bit.
That's a good point. So the volume of a gas is dependent on its container. It expands to fill the container. But we're keeping the temperature and the pressure constant. So if the pressure of the gas is constant and we put more gas in order to keep the pressure constant, we have to let the volume get bigger. If you take gas out, in order to maintain the same pressure, the container has to shrink. Does that make sense?
Yes.
So could the temperature rise and it can still maintain the same volume?
Yeah, the temperature changing can also affect it. But for Avogadro's law, we're keeping the temperature and the pressure constant because we just want to look at the amount of gas and the volume. Because in reality, all four things could change at one time, right? The amount of gas is the one that's the easiest to control, because you put it in a sealed container, right? And you don't let any in and you don't let any out. You can control that very easily. The other things are a little harder to control. Temperature, it's easy to do something at 0 degrees Celsius because you put it in an ice water bath. It's 0 degrees, it stays that way. The pressure, you can control that by using a J tube. and make sure that the levels of the liquid are the same, and then you know that the pressure's the same inside and outside. So there were ways that they did this, even, this was way before any sort of technology. It just makes it really impressive in my mind that they figured these things out. But you're right, gases do expand to fill their containers. But when a gas expands to fill its container, the pressure goes down. So if we're keeping the pressure constant, then the volume is going to have to change. Yeah, it is a little hard to think about. So let's do this one. We're going to make a table. Um, 4.8 liter sample. Okay, so 4.8 liter sample. It doesn't tell me what that is, but liter is a measure of what? Volume. So that's the volume. We know that from the unit, even though they didn't tell us. Contains 0.22 moles of helium. 0.22 moles. Well, that's our new variable N, the number of moles of the gas. How many additional moles to obtain a volume of 6.4 liters? So there's another volume. And ta-da, we have a blank in our table that we will call N2. So here's our equation. It's got fractions in it. We need to cross multiply, get rid of the fractions. So I'm going to get V1 N2 equals N1 V2. You see how that works? It's really important. Now, I'm solving for N2. Here's N2. It happens to be on the left side this time. I'm going to do the same thing I've done with the other ones. I'm going to divide by its friend here, because I want this to go away. I need N2 all by itself. If I do it to one side, I have to do it to the other side. And so I come up with N2 equals N1 V2 over V1. Then I put in my numbers. N1, 0.22 moles. Volume 2, 6.4 liters. Volume 1 goes on the bottom, 4.8 liters. And then I do the math. 0.22 times 6.4 divided by 4.8 equals 0.29 moles. Now in this question, everything's got two sig figs. Does that answer the question that was asked? How many additional moles? So we have this sample of helium gas. We have this container of helium gas, and it's 4.8 liters, and we want to make it bigger to 6.4. We have to put more gas in. What we found here is the moles of gas that need to be in the container for it to have a volume of 6.4 liters. But the question is asking, how much do we need to add? It started with 0.22, it ends up at 0.29. How much do we need to add? The difference between them, right? So 0.29 moles minus what was in there to start with, 0.07 moles added. Okay? Any questions? You always go back and look at the question. Sometimes When we read through the question, we make our table and we start calculating away and we come up with an answer. And we're like, yay, we got an answer. Let's make sure that we're answering the question that was asked, because otherwise it doesn't really matter.